Okay, let's begin our first lab in AGEC 410. We're going to talk about farm subsidies. Our topic up to date has been the sort of scope of agricultural policy. Our next topic is farm safety net. Farm subsidies are a big part of that. The purpose of these lab sessions are to give you a chance to spend have yourself be self-directed, right? So you get the material in this recording, and that way you can pause it, move back and forth between a spreadsheet. All of our work is going to be spreadsheet based, and it's just much more conducive to you getting a feel for some of the experiments or the sort of trials that we want to try out, to be sure that we're confirming things as we go along, because we are going to read and encounter things and discuss things in class that say, fairly straightforward assertions such as farm subsidies can increase output, and we're going to challenge that. But the first thing we need to do is understand why someone would make a prediction that giving a farmer a subsidy would increase output, and we're going to talk through that today. So let's think about this. So just as an introduction, let's just set up some of the assumptions or the sort of basics that might promote such an analysis. So one, producer subsidies are there to increase profits. And then the claim that we want to look into is this complaint that giving subsidies to producers will cause output to increase. And so, why would that be a complaint? Well, we'll discuss the implications of overproduction later, but in some sense, if you believe the market is providing the correct price signals, then that means it is also giving the correct signals or incentives for the production level, and to go beyond that then would move to some inefficient state. That's sort of the economic argument. We just want to examine that claim and see why the prediction is, or the complaint about subsidies, the primary complaint might be that output is going to go up. So we'll examine that. Our steps are going to be some review of theory. So this slideshow that I want to talk through is mostly some basic economic theory that we'll have to encounter. We'll use that theory to build a spreadsheet, and then we'll do some analysis. We'll pick a case and go through it. I know some of you prefer to get your to sort of learn by reading, and notes like these on a spreadsheet may not be as clear to you, and so there is a handout that supplements this, and it's there. It's short, but it's a great reference, and it includes pretty much all the example and discussion I'm going to do here. Okay, so we're going to focus on the types of support that producers may get, and we're only going to focus on two of those in this lab. So those are the ones that are based on the price. Okay, so we call that price-based support. It basically says you get an output price or an input price that you have to pay, and it's either too low if it's an output price or too high if it's an input price, and we want to change the way that price is received or is viewed by the decision maker. So you're a farmer, the soybean price is $8.50 and the government thinks it should be $8.85. There's a 35-cent subsidy. The fertilizer cost, you're going to catch me not knowing my tonnage prices, but let's say it's 5% too high. The government gives a 5% subsidy on the input purchase of fertilizer, so you're only paying 95% of the market cost. Okay, and so you get those as you choose to increase output or increase input use. You get those subsidies on the quantities. We have some other subsidy type of support that we will discuss: revenue-based, income-based, and then this decoupled historical base, which is interesting and part of this debate, but we'll leave those for another time. Okay, so to do this kind of analysis, to think about why the common complaint about a subsidy is that producers will expand production. We have to build something that is a model, right? Something mathematical that says, why would a farm decision maker choose to expand just because the subsidy is now available? Well, the simplest case, and it's tempting to just make it, is that the law of supply says that as output price goes up, supply will increase. Okay, so that's something you've had before, and it's true, and it can be confirmed. And much of what we're going to do in this lab is actually just confirmation of the law of supply. But it actually depends on, critically, you'll see as we get to the end of this, the law of diminishing marginal returns. And so we want to play the whole, play it out piece by piece, because the only way we could actually make a prediction about what subsidy level will lead to what increase in output supply is to take that apart and not just make it a generic prediction based on the law of supply. So our model is going to be a profit maximizer, someone who makes their decisions in order to get the highest profits or expected profits possible. Profits defined here will be sort of the variable revenue minus variable costs. So forget the sort of long run investment type fixed cost charges that we might normally make, and we'll just call this sort of the short run profit problem. This is a producer that takes inputs and converts those into outputs. So we need a production, what we would call production technology. So you convert inputs to outputs using some mathematical function. You do it using farm implements and labor and all sorts of things, but we are going to just make it a generic model and say there's an input, X. If you think of it as a package of input, it's an hour of my labor plus an hour of tractor time plus whatever pounds of fertilizer plus this, but we're just going to call it a single input X. It makes the math simple. And so X is an input, Y is an output, and then F is that technology. F is a function. So we'll have to replace it with an actual mathematical statement soon, but for now just let it be a function. And it's just the conversion, right? It just tells us, how do you convert the input over to output? You give me 10 of these, what number of output do you get? We need a couple other things we establish. Producers are price takers. So I'm small, I make decisions about my profits. When I make those, they do not affect the price I receive for output. By the same token, no one, when I walk into the input supply retailer, whatever, says, you are such a large buyer of inputs that we are going to change the price we're charging, right? I take prices as posted. And so basically we can say that they're market price takers. Okay, and so that's an important assumption, and it could be valid. It could be one that we want to think about later on, and we certainly will when we think about concentration and market power. Next, we need an algebraic profit equation. Before we get to sort of algebraic symbols, let's just say that profit is going to be, instead of revenue minus costs, the revenue is going to be the output price times the output quantity. Subtract from that the input price multiplied by the input quantity. Okay, so that's our algebraic setup. And now if we take that, first of all, the italicized items here, input price and output price, those are the same two things that I said we're price takers. So the decision maker that we're going to represent in our spreadsheet or in this math that we're getting ready to do is a price taker, and we're going to put those in italics to remind us that those can't be affected by the choices I make. So what can affect profits? Well, the output quantity can affect it, and the input quantity can affect it. Okay, so let's move on. Let's make new symbols now. So I'm going to represent that output price by capital P, that input price by lowercase r, the output quantity by capital Y, and the input quantity by capital X. And then I'm going to replace profit with just the capital Z. And so if we substitute all of these, then you'll have an equation that says Z is equal to, that says Q. it should say y. Z is equal to PY minus RX. Okay, so profit equals revenue minus cost. And now we are in a place to think about our equilibrium conditions, the so-called marginal balance conditions that let you decide what is the best choice of output by a producer. And you may remember it. Marginal revenue equals marginal cost determines the best choice of a producer. And I'm sure you've seen this in your farm management or agribusiness management class, where they tell you the change in profit, the change in cost, and you keep going. You keep adding units of input or new units of output until those balance each other out. The next unit causes a change in cost that is just balanced off by the change in revenue. Well, in economics, sort of continuous algebraic economics, that means the change in this term gets balanced against the change in this term. And if those two things balance each other out, then it must be the case that profits can't go up any further. Okay, so think about this. If we make some change and the revenue term goes up, the input cost term goes up as well, but not by as much as this, we just gained profits. That next unit, the revenue gain, exceeded the cost gain, profits went up in total. If the last unit of profit gain, or revenue gain, is exactly equal to the last unit of cost gain on this term, then profit change is 0. So that gets us to calculus. And we're not going to do the calculus. I'm going to present the calculus, and then we're going to let the spreadsheet do the calculus. But if we're going to use that term marginal in an economic statement or condition, then we have to recognize that calculus was involved, and we should be able to work with it at least symbolically, right? And it's going to help us sort of separate this out. So rather than having to point to the revenue term and the cost term and how they might change, we can actually get to what those derivatives or those actual changes are. So let's do this step by step. So we started with this revenue equation. I've corrected the y here. So profit is revenue minus cost. And now y is actually determined by how much input we use. So if the production technology is defined as y, the output, is equal to some function of the input x, then it must be the case that when you tell me the input level, I just feed it through this function and I know the output level. And so that means that we can make a substitution so that profit is equal to price times this outcome of the production function minus the input price times the input quantity. And that's where we're ready to do our calculus. So we have calculus that can be applied to the variable that we choose, x, and we'll end up with this. So dz over dx, that's just a derivative, right? That's the symbol for a derivative, and we'll just say it's it is exactly the change in profits per unit change in input. So z is the change in profits, dz is the change in profits, dx is the change in inputs. So this is a rate. It's how much do my profits change when I increase input use by 1 unit. On this side, we now have that change in revenue term. So the change in revenue from using an additional unit of input is measured right here. P times F. That prime just means a derivative of the production function. So PF prime of X. Just think of this term as marginal revenue. That's all we need to know. And then on this side, we have the change in cost when I increase input use by 1 unit, right? If I order 10 units today, and then when I go to pick it up, I say add 1 more unit. If they're pricing me the same for every unit, which is our assumption, then that change is just going to be R. The change from what I previously ordered to what I actually took home is just going to be the cost of an additional unit. So R is that input. And then we put this 0 on the right hand side. So if you remember your basic calculus, we were trying to find the peak, right? So you have a function that has some kind of arc to it like this, and then the inflection point at the top. the critical point at the top is where that function levels off and changes to negative. Well, think of it this way. Profits increase when you use input, and at some point profits peak. And to continue to use them beyond there would be to lower profits. Well, at that peak, then it must be the case that that derivative for profits is equal to 0. If that's the case, right? There's a horizontal line there saying the change in profits is now 0 at this top point, and that's what defines this equation. So marginal revenue minus marginal cost equals 0, or if you prefer, grab this minus R, move it to the right hand side, and you get a plus R, and it says the marginal revenue of adding an input unit is exactly equal to the marginal cost. And you can see those compared here. So the marginal gain to revenue, adding an input unit. The marginal change to costs from adding an input unit. So we are pretty far into this. Again, you know, I'm not going to ask you to reproduce this stuff. I'm just going to ask that you understand that what has to be considered when we think about a decision maker is they are going to balance off changes in revenue against changes in cost, and they will make a choice that reflects that balance, right? The last unit I applied cost me the same as it generated in returns. Why do we do that? Because to use any less input would have left profits on the table, right? There were gains that I left off that I could have had. So that puts us to the final sort of steps of our analysis. I think we have a couple slides maybe here to go. But we haven't had any policy so far. And so what we need to do now is add a subsidy. So instead of just being the price per unit, right, let me back up. Instead of it being price times the output, what we need now is I get the price from the market times my output, but I also get the subsidy rate times my output. So I tell the government, I tell my local FSA office, I produced 500 units, I sold it. They don't care what the price is, but they will tell me that 500 units qualifies me for a subsidy, and they will tell me that 500 units times that subsidy is a certain amount, and that's the check I should expect to receive from the Commodity Credit Corporation when they pay out farm subsidies. And so now, in terms of the price I get from the market, it is still P, but the total receipts I get, the total revenue I'm expecting, depends on the price plus the subsidy. And so if we wanted to, we could go back to this, the change in revenue here, the change in cost, and if we're going to account for the total receipts, then it must be the case that this term, this mathematical term, should include the price plus the subsidy being multiplied by F times X, the change in output. And so now the per unit change in revenue goes up if that subsidy goes up, and then the per unit change in cost stays the same. This side of the equation, this piece, is not going to be affected by the output subsidy that I'm talking about here. Okay, let's rewrite this. So if this is what the new condition looks like, marginal cost on this side, marginal revenue or marginal receipts on this side, and the subsidy is 0, then that term just goes away, that S goes away, and it's just price times the output change gives me balanced off against the input cost. But if we start increasing S and make it something that isn't 0, and R is on the right hand side here, not allowed to change, then it must be the case that this term in brackets is getting bigger. The term on the right, F prime of X, has to get smaller. It's the only way for this to work, right? So if you make this term bigger, then the only way to keep it constant on the right hand side is to make the term you're multiplying by smaller. Okay? And so it must be the case then that increasing subsidies must cause that term right there, F prime of X, to fall. If this equation is going to hold, and again, it rests on the assumption that we are profit maximizing producers who take R and P, the output price and input price as given, but if that's going to hold, then that marginal product, f prime of x, must fall. Okay, why do we expect that to be the case? Right. So we've now uncovered the condition that would cause someone to believe output is going to go up when you increase the subsidy. Well, it's from the law of diminishing marginal returns. You add a unit of input, you'll get new output, you'll get a higher level of output, but the gain is not as much as it was for previous units of input. And so if you remember your law of diminishing returns, it can be summarized here. The first unit of input adds more output than the second input unit you add. The second unit adds output, but it doesn't add as much, but it doesn't add as much as the first, but it adds more than the third, and that is the law of diminishing marginal returns. The implication here is then that if you are adding a subsidy to this, making it from 0 to some positive number, you are forcing the marginal product to fall, then it can only happen that f prime of x, that is the marginal product, that is the marginal return in output terms. The only way for that to happen is if you added more input. And if you add more input and you plug it into the production function, we expect it to increase output. And so that is where this law of diminishing returns, which is implicit in the law of supply, is what tells us that adding a subsidy should cause a producer to use more input. That will lead to more output, and we expect price to go up. So basically, adding a subsidy should have the same effect as if we just applied this law of supply and told the and if a producer expects the price to go up, they produce more. That's the law of supply. We believe it. But if a producer expects that they're going to get a subsidy, then they should also produce more. It's just the right thing to do. It's just optimal. Okay, so we've laid out the theory. We'll continue to discuss that in class, but now what we want to really do is sort of, given our positive economics training, we put we posited some theory. It all kind of makes sense, and let's do some calculations. Let's do a test and see if we can build a quantitative model in a spreadsheet that will confirm it. And so we're going to do that in a spreadsheet. I'll open my spreadsheet up here in a minute. I'll put it together cell by cell with you, and then I'll leave it to you to we'll do a little bit of analysis, and then I'll leave you some questions that you can do for the quiz in this lab. So the spreadsheet model, step one, we're going to do the static calculation. If you read the handout for this lab, which you can do it before or after you watch this video really, but if you read that, you'll see that we have a sort of a base or static calculation that has a prediction on the impact of a subsidy that we expect to be wrong. We expect it to underpredict how much subsidies would cost and how much output change would be there. Step two, we're going to build the predictive model, and that's the one I'll add the formulas and show you step by step. And then we're going to use solver. We don't want to do calculus. We just want to use solver, and I'll give you a way to confirm that you've correctly built the spreadsheet. We'll use solver for a couple of tests, and then we'll compare the subsidy costs and output changes and see that we need to understand economics, and we need to understand how producers behave if we're going to have anything to say about what subsidies mean and what subsidy costs will be and how they might affect output. We can't just take what's the subsidy rate, what's the output level, and do that calculation. So I'm going to switch over to the spreadsheet. You can go ahead and download and the lab spreadsheet and open it, and that's where we'll begin from next when the screen switches over. Okay, if you open the lab included with the spreadsheet, the spreadsheet included with the lab materials, you'll see it has this column that's called static, and that's the one I want to start with. And so we're going to use that same simple example. I think it's better to use made-up numbers first, and then we'll start digging around and think about what the impacts would be when we dig a little more into how subsidies are kind of arranged in the wild, so to speak, in U.S. ag policy. But let's learn a basic subsidy approach right now. and then we'll save for later labs digging through what those impacts may be for U.S. producers under the current rules. So I've got some sections here: prices, quantities, policies, and then outcomes. The prices are going to be fixed, right? So whatever we start with here, they should stay. And so you can see I've just typed in numbers for the assumption. So the output price is going to be 1, the input price is going to be 2. For the quantities, if you read through the lab handout, I said there were 25 units of input and 100 units of output. Okay, and so we are missing one thing there that we added in the, you read through the handout, you'll see that we add a production function, but if you the slides we just went through, we said, well, we need to figure out what the formula is, or the mathematical equation that converts input to output, and we'll do that in the second column over here under the lab model. But for now, let's just take 25 units of input, 100 units of output. Now we have two cells here in the policy section, so we're going to have an output subsidy and an input subsidy. And those are just zeros now. Those will also be set away from the producer. Okay, these are going to be the rates of subsidy. So the producer doesn't get to pick their subsidy rate, but the government sets those, and then they choose their production based on not just the market price they expect, but also what they think the subsidy that's been announced for them will be. And then finally we have our outcomes, and these are the things we want to track. So we have the revenue, which I've calculated here, and you can see the cells that go into calculating the revenue. It's B3 right here, the output price, times B7, the output units, plus B11, the output subsidy, times B7, the output units. Okay, so we got two terms. The first term here is how much do you sell this stuff for, and the second term, how much do you get in revenue from the government. Okay, let's do the same thing for an input subsidy, and it's going to be a little bit different because we pay for these, right? And so if I'm a purchaser of inputs and you are subsidizing me, you are taking away some of the cost that I would pay for that. So that's going to be a negative to cost when we get an input subsidy. And so you'll see here we have B8 used twice. That's the input units right here. B4 is the input price. B12 is the input subsidy. So we'll calculate the actual cost I pay to the market, B4 times B8, the market cost of inputs. And then from that, when we calculate profits, we want to take away the government subsidy that is based on my input choice or my input purchases. So if they're giving me 10 cents per hour that I work or something like that, then that is a reduction in my cost, a reduction in the charge that I might pay. If you one of the things we've talked about in class, if you wage work, if you have to hire workers to come on the farm, you pay the full cost, but the government reimburses you through some kind of a program for part of the payment for that labor you hire, then that would be a reduction in the actual bill that comes off there. And then finally, profits is just going to be take the revenue, subtract from that the cost, and you get the profits. Okay, so we have a static model. We call it a static model because we're not going to let decisions change. But we can play around with what happens if policy changes. And I think the example from the lab says, what if it's 5 cents per unit? So it's like a 5% subsidy, so to speak. You got an output price of 1. You add 5 cents coming from the government's going to pay you for every unit. And then you get this prediction here. You get $1. Now you get $1.05. The 100 units are now worth 105. The input costs did not change, 25 times 2, and the new profit level is 55. So that's going to be our benchmark case. Now we believe that's wrong because we expect the producer, when they are now offered not just $1 right? The revenue down here is a $1.05 per unit, not $1 per unit. So now they can see $1.05 coming per unit. So we expect that they will want to increase output. The only way to increase output is to increase inputs. And then that's going to have some effect down here. Our profit prediction, our revenue prediction, and our cost prediction are all going to be off, and so we need to see how that's going to work. So this is the part where it gets tricky, so you may want to pause and be sure you add some things. But I'm going to build out the lab model here right down this side. I'll show you, I'll type in every formula as I go, just so that you can check it all. Okay, the first thing we're going to do is we're going to still be price takers, so the prices are going to stay the same up here. The output price of 1, the input price of 2. We can start from the same input quantity, right? That's going to be something that we let the producer choose. For us, in the lab model, it's going to be the choice variable. It's going to be the thing that we move around to try to make profits as large as possible. Some other things that we're not going to change. Well, for now, let's put the subsidy rate for output and the subsidy rate for input at 0. And then down here, the revenue, the cost, and the profit, we're going to calculate all those the same way. So you can just highlight those, hit Control-C, and then paste them over. Okay, and you get the same formulas here. Now, what has happened is I don't have any output yet to add it to this model, so I don't know. So right now I'm paying cost, but I'm not getting the output, and so that's because I need to add my production function. Okay, so what is our production function going to be? Well, it needs to be a function that turns 25 units into 100 units, and as much as the temptation is to just say 4 times 25, that is not the production function we're going to use. So I want to add it right here. And so to add a formula into a spreadsheet, just if you haven't done it in a while, remember you type equals. So if you start something with an equal sign, then Excel expects to get a formula following that, and then it'll do the calculations on that. Okay, so we need our formula, and I'm going to make the formula be $20, and then I'm going to type Shift 8, so you get the asterisk for multiplication. And now we're going to use the input quantity, so it's going to be 20 times the input quantity, and then this is the tricky part. It's going to be actually Shift 6, and that's how you get an exponent. Okay, and then we're going to make a parenthesis 0.5. I think that'll work. So what is this formula, or what is this production function? It says take 25, the input quantity, to the 1/2 power, then multiply it by 20. Or if you remember, the 1/2 power is like taking a square root, so we could have used the square root function there. Take the square root of 25, multiply it by 20, and that should be our input level. And that's what we got. And so if you would prefer, I believe the square root formula is this. Yeah. And so you could do this equals the square root of that, and that would be the same. That would be the same type of formula to put in right there, instead of raising C8 to the 1/2 power. That's not what I did though. Okay, so now we've got 100 for the output, 25 for the input. Everything matches up here, and so let's just add our subsidy and see what happens. Okay, I promised you one thing and it didn't happen, right? I promised you that we would build a lab model that would not be static, that would say when you get an extra 5 cents of subsidy per unit compared to 0, what it was before we typed that in, that this stuff was going to change. And so we need a way to make that change. And we have a way. And we're going to use calculus, but we're going to let the Excel program do the calculus for us. So let's take that away real quick. Let's make that 0 again. And I want to introduce you to Solver. And for many of you who've had AGEC 352 or even something before that, or just on your own, it won't be new, but we should do an introduction to it now because we're going to use it a few times. So if you click on the Data tab up here, all the way to the right, scrolling across here in Excel, you may or may not see Solver and then something called Data Analysis. So Data Analysis has a bunch of statistical tools. Solver has a bunch of sort of choice or mathematical tools for doing calculus. And if you don't see the Solver there, let me make a suggestion to you. One, you could Google and see what it says to do, but also you can go to File, Options, and then you should see something like this, and it should have something called add-ins. And if you click on add-ins, and then down here it says Excel add-ins, or right here it says Solver add-in, what I usually do is go to the Excel add-ins, click on Go, and then you should see some boxes like this. And if you don't see Solver up there, it must be because that box right there is unchecked. If you just will check it, just check that Solver add-in box right there and click OK, then you should see Excel do a little bit of work and it'll just add that for you. That is a preloaded software package, but it is not a standard load, right? So when you install Excel on almost any machine, Solver does not install as part of it. It leaves that sort of hidden or just unexpressed, and then if you want the add-ins, you go and pick which ones you want. So again, moving to the top here, that's on File, Options, Add-ins, Excel add-ins, Solver. And then when you're on the Data tab, it's possible if you have a different version of Office than we have in our offices here at Purdue, Solver could be in a slightly different place, but the key thing is to find this analysis grouping on the ribbon, I guess is what it's called, and then choose Solver. Okay, so we have this column here. It's not doing exactly what was promised, and so let's make it do what was promised. So let's go to Solver and look a little bit here at what the setup is. Okay, so we'll learn a little more about this as we move on, but for now, the objective, that is the place where we say what is the target or the goal or the decision maker that we're trying to represent here. What are they trying to do? Well, we know that we called them profit maximizers. They're trying to make profits as large as possible. And so that means B17 is really that target. That is the number, that is the value that they want to be as large as possible. And so I'm C17. So I'm choosing C17 as my objective cell. And then this row right here says, would you like that to be large? Would you like that maximized? Would you like it to be small, minimized? Or would you like to hit a target value with it? And we're only going to do this. So we're going to click on this button to choose for a maximum. And then it says right here, what variable cells would you like to be allowed to change? And we have only one, and that is the input unit quantity. So we want to let we want Excel to make adjustments to the input choice based on what will give profits their highest level. Okay, so we're saying take C8, the numbers or the values in this cell, make adjustments to those until you have found the highest level for C17. And that's what we have. So this checkbox should be checked. It says make unconstrained variables non-negative. And then here is something called the solving method. We don't have to know too much about that, but you'll want it to be GRG nonlinear. If it doesn't say that, click this drop down and make sure that you switch it to GRG nonlinear and click solve. Okay, that ran off my screen, but here it is. It says solver found a solution, optimality conditions are satisfied, and I can choose to keep it. So what we've established at this point is, if there are no subsidies on output, then $50 is the best profit, and 25 units of input is the best choice for input level. So now we have to go back. We're going to add our subsidy, 0.05. That's a government payment. Solver updates the predicted revenue, cost, and profit. Excel updates the revenue, costs, and profits to the static case, but we have not allowed Solver to make changes. When Solver sees now that this is 0.05, that this revenue prediction is 105, is it going to want to change 25 on behalf of the producer that we're modeling or not? And so we click on Solver again. We keep the same things though, the same setup. C17 is the profit, C8 is the input choice, maximization is the direction we want. So we click on Solve, and now you can see that we have confirmed the supply increase prediction. So what happens? I'm going to just keep that solver solution. I don't want to see anything else. The static prediction was 25 units of input, 100 units of output, a profit of 55. This producer, once you offer them a 5-cent subsidy, really 5% of the output price, with this production technology can use 2.5 more units of input, about 10% more units of input. They get about 5% more output, and then they get $5 extra of revenue, something slightly less than that, $5 and a quarter increased revenue, $5 and an eighth increased costs, and that leads to the profit level being off by 1/8 compared to the static case. So they get the full $5 that we expected, plus they get 1.25 in profit. In additional. An eighth of a dollar in increased profit. So, what does this mean? Well, the actual subsidy cost here we thought was going to be $5, and instead it's going to be something larger, right? The profit gain is going to be something larger. But the critical part is that we truly did confirm this prediction that if you offer them a subsidy of 5 cents, you're not just going to pay it on 100 units, you're going to pay it on 105 units. Okay? And so if this stuff, let me just check, if you go to format cells, if you don't like that, you can just cut it off at 2, so you're 105. I believe it'll be okay for these too. Format cells. So we've confirmed that it's not just that you're going to pay 5 cents per 100, you're going to pay 5 cents on 105 units, because those producers, they're not going to stop. They're not going to keep the status quo. You tell them they have a 5% gain in price that comes from the government, and it's per unit. Well, then the objective is to make some small increase in the output level from 100 to 105, and get the extra revenue out of this model. Okay, so what else could we do? Well, we could try larger levels of profit of subsidies. So what if it was a 20%? a 20% subsidy. You type it in. You could compare, point 2. You could compare the prediction here, but to get the comparative prediction for the lab model, don't forget you have to go back over here to solver and resolve. Okay, so the static case says profits will be 70, revenue will be 120, when in fact under the new case of a 20-cent subsidy per dollar, output is now going to go up to 120. Okay, and if you want to know what the government pays, right, it's that times that, so $24. So a subsidy we thought was going to cost $20, we undershot it by $4, right? It's going to be $24 just because there's going to be an additional 20 units of output just from producers responding. Okay, that's our basic setup, and so you should be able to, if you can't confirm this set of results or the previous one we had with 5 cents per dollar on the output subsidy, then you please go back in the video and check as these things are entered. Remember, you can use the square root formula here if you prefer, but that is the exact formula as it needs to be typed, as long as you're following along with everything I've done here. And then you have a couple of questions that you need to post to show that you've been through the lab and you have a finished spreadsheet. So just a little online quiz that checks your work and lets you just kind of put in some multiple choice answers. Okay, with that, I'm gonna end this. We've spent about 45 minutes of class time here, and hopefully it hasn't taken you too much extra time, but that's why we did it online, so you could go at your own pace. So move on to your quiz for this lab, and then we'll meet up in class and we'll continue on this topic a little bit.